I'm wondering about whether there aren't microbes that do break down glyphosate. Is there a biological community that can work on this stuff so that when it comes out, it eventually disappears?
There are organisms that can utilize it as a nutrient source. Fusarium is one of them. There are several others. The problem is that they're not predictable. Work in the laboratory and you can trace it all the way down to carbon dioxide and nitrogen, phosphorus. The problem in the field is that it's not predictable, and most of the degradation in the field occurs by a route similar to what DDT degrades by. We call that co-metabolism, where the organism just happens to produce some enzymes that will decarboxylate and break it down. Especially the most common breakdown is just decarboxylation, taking off one carbon off of it. It leaves the AMPA as the first degradation product that is every bit as toxic for plant growth as the glyphosate is. That's one of the reasons why there are three enzymes that they could engineer into the Roundup Ready plant that would degrade the glyphosate. All three of them leave a product in the plant that kills the plant. And that's why they're not engineered to break down the glyphosate in the Roundup Ready plant. But there are those organisms that can do it. It's just that so far they're not predictable, but there are several laboratories now that are screening and developing organisms that can, with the idea of using them kind of as a probiotic or as a remediation effort. And some of those trials look really promising. They look very good. So there's some good research going on as far as that soil residual. It's just been considered such a benign entity in the past, nobody worried about it. I think in a relatively short time, a few years, those organisms are going to be available for remediation. So that's other questions in that area. Again, the increase in disease, what we've done is we've increased the virulence of many of our pathogens, especially Fusarium, Rhizoctonia, and the Pythium phytophthora-phanomyces type pathogens. So that we live with those all the time. And then when you change that soil biology, we also lose that natural biological control that we used to have, as well as the nutrient control, as I mentioned, with the Roundup Ready versus the normal corn as a pre-crop for potatoes. You'll see I had 50 growers that asked me to analyze their data and tell them what was ask me what was going on. I thought when I looked at the data, you have a group that is still producing over 35 to 40% of their crop, over 10-ounce potatoes. Good market size, acre size potato. You have about half of them that used to produce 35 to 40% of their crop over 10 ounces, that have dropped down to about 20 to 24% of their crop in that range. And then you had a group that had dropped down for 5 to 8% for 10 ounce. Everything else was down in the very small 6 to 8 ounce or the cold potato. You know, the companies are pretty smart. They won't let the grower, at least in Idaho, told the grower they can't spread out their chains on their picker, but they don't get paid for the coals, anything that's under a certain size. So they can run those in for starch production or processing, those little ones, anyway, I had 3 petio analysis, I had a soil analysis, I had all of their crop rotation schemes, and essentially they're all the same. I had 37 of them that were all west of Burbank. All of them had corn, it was a pre-crop. When we finally got smart enough, after fussing with the data for a couple of months, to ask for what the herbicide program was, we found that those that hadn't used glyphosate on those soils, on those fields for the previous 2 years, were still doing like they'd done for the previous 30 or 40 years, at over 35%, over 10 out. Those that had used 1 or 2 applications of glyphosate in the previous 2 years had cut their bulking in half. Those that had shifted to the Roundup Ready corn were in that 5 to 8% bulking, because it also changed very dramatically through those root exudates. That soil biology that kept the nutrient levels up from a crop rotation, crop sequence standpoint. Again, the diseases that we've seen increase, you change that overall management aspect that you have, that you've relied on or that you've developed in your own system when you start making these changes. Again, you can't change just one thing without changing the interaction of all of those other systems. This is some research of Dr. Robert Bremer. You can see this Roundup Ready soybeans, a 500% increase in fusarium root colonization when you put a little glyphosate on the foliage of those Roundup Ready soybeans. Doesn't kill them, but it sure changes those components in that ecology that we manage. You see the effect on the manganese-reducing organisms that make manganese available as that critical element for photosynthesis and for disease resistance in the shikimate pathway. In fact, the normal plant enzyme requires manganese as that key to the ignition to turn the shikimate pathway on, the EBSPS enzyme on. The bacterial pathogen that's in, or enzyme that's inserted in the genetic engineering process doesn't require it. It requires magnesium, which is at a high concentration in the plant. We measure it by percentage, so there's enough there to keep it functional in most of the tissues. When you go a deficiency of magnesium, you also shut down the bacterial EBSPS, and you see some damage, direct damage from the glyphosate then. But you see that interaction. Again, there aren't any voids in nature. When you take one out, you increase something else. Worked on biological control. I've had a number of organisms that in the greenhouse really look great for controlling these soil-borne pathogens. Put them out in the field and get inconsistent results. But fumigate the soil, and then add them, I get some really good results with it. The problem is you've got a biological buffering capacity in that soil that's very difficult to overcome. And that's why biological control for these soil-borne pathogens has always been erratic, because we haven't been able to outcompete a lot of those basic organisms that are already there. Same thing with nitrogen fixers, with your rhizobium, radiorhizobium. We have strains that you can select that will increase nitrogen fixation by 3- and 4-fold. But most of them can't outcompete with the natural organisms in the soil that have been established over the years. And so you don't see that response in the field. Maybe one thing in these glyphosate soils where we're seeing that the rhizobium and radiorhizobium aren't able to survive, that it may give us an opportunity to go back in there. The problem is we have a high oxidative population that provides that biological buffering. But Chris Ellsworth retired a year before I did, and I may have mentioned this yesterday, but in his retirement seminar, he kind of recounted all of the things that he had done at Purdue University for 40 years as an agronomist, and he said my first 15 years, I worked on legume inoculant. After 15 years, wasn't any benefit because they were established in the soil and